What specific problem does the Magenta RT method aim to solve in the context of live music generation?
The Magenta RT method aims to solve the problem of real-time audio generation for live music performance, addressing the limitations of existing generative AI systems that primarily focus on offline turn-based generation. Specifically, it seeks to achieve a real-time factor RTF of at least 1, enabling continuous audio streaming with low latency, which is essential for interactive live performances. By employing a chunk-based autoregressive approach and utilizing a coarse representation of audio context, Magenta RT ensures that users can input control information continuously while receiving an uninterrupted audio stream. This method also emphasizes the importance of responsive controls, allowing for dynamic user interaction and personalized expression in live music settings. Overall, Magenta RT represents a significant advancement in enabling high-quality, real-time generative music that can adapt to user inputs seamlessly.
How does the proposed Magenta RT algorithm work? Illustrate the process step by step, including the role of the codec language modeling and the music-coca embeddings.
The Magenta RT algorithm operates through a series of steps that leverage codec language modeling and music-coca embeddings to generate high-fidelity audio in real time. First, it utilizes the SpectroStream codec to convert raw audio into discrete tokens via an encoder, which compresses the audio data while minimizing distortion. Next, the model employs a joint audio-text embedding mechanism through music-coca, which creates style embeddings from both audio and textual descriptions, allowing for high-level control over the generated music. During inference, the algorithm predicts audio sequences autoregressively, conditioning on both the previous audio tokens and the style embeddings derived from music-coca. Finally, the model generates an uninterrupted audio stream by employing chunk-based autoregression, which processes audio in 2-second chunks while maintaining a context of the last 10 seconds, ensuring real-time performance with a real-time factor RTF of at least 1.
Can you provide a simple yet illustrative example of how the proposed Magenta RT algorithm generates audio, detailing its interaction with user inputs and the resulting audio output?
The Magenta RT algorithm generates audio by continuously interacting with user inputs through a process called audio injection. For example, a user might provide a live audio input, such as a melody played on an instrument. At each generation step, Magenta RT mixes this user audio with its own generated output, tokenizes the resulting mix, and uses it as context for the next audio generation. This allows the model to adaptively respond to the user's input, either by repeating, transforming, or incorporating features from the user audio, while also maintaining the desired style based on the conditioning provided. The output is a seamless audio stream that evolves in real time, reflecting both the user's contributions and the model's generative capabilities.
What are the theoretical and practical benefits of using Magenta RT over existing offline music generation models like MusicGen or Stable Audio Open?
Magenta RT offers several theoretical and practical benefits over existing offline music generation models like MusicGen and Stable Audio Open. Theoretically, it achieves real-time generation with a real-time factor RTF of 1.8, allowing for continuous audio streaming, which is essential for live performance settings. Practically, it utilizes 38% fewer parameters than Stable Audio Open and 77% fewer than MusicGen, making it more efficient while still outperforming these models in automatic music quality metrics. Additionally, Magenta RT supports responsive controls and causal streaming, enabling users to interactively influence the audio output in real time, which is not possible with traditional offline models. Finally, its open weights architecture allows for on-device inference, providing lower latency, higher reliability, and enhanced privacy compared to cloud-based solutions.
How was the Magenta RT method validated or tested, particularly in terms of the metrics used to assess its performance compared to other models?
The Magenta RT method was validated through a combination of subjective playtesting by team members and partner musicians, focusing on the expressiveness and engagement of the instrument. Additionally, more constrained experiments were conducted to assess core capabilities common to both live and offline music generation models, such as audio quality and adherence to text conditioning. Specifically, the performance of Magenta RT was compared to prior models using established metrics, including the Frechet distance based on Open L3 embeddings, FD Open L3, Kullback-Leibler divergence KLPASST, and clap score. The results indicated that Magenta RT achieved the lowest FD Open L3 and KLPASST scores, suggesting that its generated audio closely matched the reference audio in terms of plausibility and semantic correspondence. Furthermore, the clap score demonstrated that while Magenta RT performed well, it scored between other models, indicating a competitive adherence to specified text prompts.
What limitations or drawbacks does the Magenta RT method have, especially regarding its implementation in live settings or the quality of generated audio?
The Magenta RT method, while innovative, has several limitations in live settings. Firstly, achieving a real-time factor (RTF) of at least 1 is challenging, as it requires efficient processing to maintain uninterrupted audio generation, which can lead to potential latency issues if not managed properly. Additionally, the use of a coarser representation of audio context for conditioning may compromise the fidelity of the generated audio, as it relies on lower quantization levels that might not capture all salient acoustic details. Furthermore, the model's reliance on a limited context of previous chunks, only 10 seconds of history, could result in error accumulation and unpredictable behavior during longer performances. Lastly, while the audio injection mechanism allows for user interaction, it may not always produce the desired transformation of user audio, as the model's output is influenced by its own predictions rather than directly incorporating user input.